math, it's all about math, the wonderful world of math. Welcome to the wonderful world of math. In today's adventure, we explore the cosine sum angle identity. So the cosine sum angle identity tells us what to do with the cosine of a sum of two angles. So if we have cosine of an angle plus another angle, we can use this cosine sum angle rule. Now we're not going to derive this identity in this video. That's a whole other thing. This one, though, we can use, and we can use actually to get the other identities in a relatively easy and, in fact, helpful fashion. Coming up with this identity requires a lot of geometry and some trigonometry, and isn't super helpful to us for using these identities. But we can use this one to get other ones, and that is helpful for us learning to use these identities. So let's give our first example of how to use the cosine sum angle identity. Let's say that I want to find the cosine of the sum of these two angles, 30 degrees and 45 degrees. For one thing, we should be able to see that the sum of these two angles is easy for us to do, and that you'll end up with 75 degrees if you add 30 and 45 degrees. But we don't know the cosine of 75 degrees, right? So one of the things the cosine sum angle formula is helpful for is taking the cosine of an angle that we don't know and expressing that angle that we don't know as a sum of two angles that we know better. Because if you look at the formula, this identity takes the cosine of a sum of two angles and breaks it down into cosines and sines of the two separate angles. So let's compare this to our formula. We see cosine of the first angle plus the second angle is the cosine of the first times the cosine of the second. So here we have the cosine of the first angle plus the second angle. First of all, this will be the cosine of the first angle, that's 30 degrees, times the cosine of the second angle, that's 45 degrees, minus now the sine of the first angle, 30 degrees again, times the sine of the second angle. And the second angle is still 45 degrees. And again, while we don't know the cosine of 75 degrees, we do know the cosine of 30 degrees, and the cosine of 45 degrees, and all the rest of these. We know those. So what is the cosine of 30 degrees? If you said root 3 over 2, good for you. The cosine of 45 degrees. Okay, you get it? The square root of 2 over 2. The sine of 30 degrees, 1/2. And the sine of 45 degrees, we get this. Now remember that multiplying fraction means top times top over bottom times bottom. Remember also that the square root of 3 times the square root of 2, just like any time you take a product of two real square roots, this is equal to the square root of the product. So the square root of 3 times the square root of 2 is equal to the square root of their product, 6. So root 3 times root 2 means root 6, and denominator times denominator, 2 times 2 is 4. On the other side, 1 times root 2 is just root 2 over 4. Now these guys have a common denominator, so we can take this difference of two fractions and write this as a single fraction with the difference of the numerator up top. And this is how we want to write our answer. So to recap, the cosine of 30 degrees plus 45 degrees is equal to this. It is also equal to the cosine of 75 degrees. So in the future, I can ask you for the cosine of 75 degrees. You know that 75 degrees can be written as the sum of these two better known angles, and that we can use the cosine difference angle identity with this sum. Okay, cool. Cool. So for our second example, let's suppose I ask you for the cosine of 195 degrees. In this case, we don't know how to do 195 degrees, right? That's not one of our favorite angles. But with a little bit of a look back at what we did last time, we see that maybe if I can write 195 degrees as a sum of two easier angles, I can use that sum angle identity to help me out of this jam. So, what are two angles that we're more familiar with that add up to 195? Last time we added 30 and 45 degrees, and we got 75 degrees. What we're looking for are angles that are 30 degrees, 45 degrees, 60 degrees, or things that are in other quadrants that have the same reference angle. So maybe we don't want 45 degrees, maybe we want someone in the second quadrant that has the same reference angle. If this is 45 degrees, who's over here that has the same reference angle? Well, remember how reference angles work in the second quadrant. If this reference angle is 45 degrees, and this is the angle we want, we know that these two guys together add up to 180 degrees, right? Theta, the one we want, plus the reference angle, theta prime, adds up to 180 degrees. If the reference angle is known to be 45 degrees, then we know that theta is going to be 180 minus 45 degrees. So I don't just want to try 30 and 45 and 60. Sometimes it's also helpful for me to add 135 degrees and something else. In this case, you'll notice that why am I putting it there? I left a space just for this. 135 degrees plus something will equal 195 degrees. And that other something is a pretty nice angle. So while 135 isn't as easy for us as 45 degrees, 135 degrees is still a really pretty easy angle, compared to something like 195 degrees. This is only one way to add two better known angles up to equal 195 degrees. Can you think of a second way? Look through all of the angles on your unit circle that we use frequently and see if you can find another pair that adds up to 195. Did you find one? If not, pause this. I can wait here, right? Just pause me. Find it. 3, 2, 1. 45 degrees and 150 degrees also add up to 195. Now, either of these things will get you the right answer, and you only need to do one of them. I'm going to do the first one, and I'm going to suggest that after I do it, you try doing this identity on this one and verify that they in fact give you the same answer. So we have the cosine of a sum of two angles. So calling up that cosine sum angle formula, we're going to get the cosine of the first angle times cosine of the second, minus sine of the first angle times sine of the second. Cosine of the first angle means cosine of 135 degrees. Cosine of the second angle means cosine of 60 degrees. So we get cosine of 60 degrees. And the sine of the first angle means sine of 135 degrees. And sine of the second angle means sine of 60 degrees. We see how we're substituting this angle in for this angle and this angle in for this angle? Great. Now once we've got that, we just need to evaluate. Because we know cosine of 60 degrees, we can replace this cosine with its value. Cosine of 60 degrees is 1/2. Cosine of 135 degrees. Well, let's see. 135 degrees is in the second quadrant, and cosine is negative in the second quadrant. Its reference angle is 45 degrees, and cosine of 45 degrees is radical 2 over 2. Sine, however, is positive in the second quadrant. So this sine of 135 is exactly the same as the sine of 45 degrees, radical 2 over 2. And then the sine of 60 degrees, radical 3 over 2. Multiplying fractions means top times top over bottom times bottom. And this becomes negative root 2 over 2 times 2. And this is negative root 2 times root 3, negative root 6, over 2 times 2. So for our final answer, we combine those two fractions into one fraction, and this is the cosine of 195 degrees. We're going to do one more before we move on to the next video. Cosine of 7 pi over 12. This time it's in radians. So we're going to ask, is there any way I can write this as the sum of two angles in radians? The easiest way to think of this, to stay within radians, not have to fall back on degrees as a crutch, is to think, what are some ways I can add up to 7, right? If you've got 7 pi over 12, you want to be able to write this as fractions with a common denominator being added. So 6 and 1 add up to 7. And 2 and 5 and 3 and 4. These are all the ways to add numbers up to 7 without having to use negatives or fractions or anything like that. So 1 plus 6, 2 plus 5, 3 plus 4, 4 plus 3 is just the same over again. So this is it. Do any of these reduce nicely to angles that you know better? 6 pi over 12 does. It's pi over 2. But this doesn't help my picture, right? I can't say, well, this angle is super nice, but this one's a problem. I'm going to do this. No. 2 pi over 12. That also reduces. What is it? Ding! Pi over 6. Right? There's a common factor of 2. You reduce it. This is pi over 6. This is a nice angle. This, though, is not. 3 pi over 12 reduces. They have a common factor of 3, leaving you with pi over 4. 4 pi over 12 also reduces. This is the only one where both of the summands will reduce. 4 pi over 12 becomes pi over 3. This is one where I actually know both angles. So you see, I didn't have to start out knowing that pi over 4 plus pi over 3 was 7 pi over 12. All I did was look for different ways to add up to 7. 1 and 6, 2 and 5, 3 and 4. And I made sure that they all had pi on the top and 12 on the bottom, so that they would be adding up to 7 pi over 12. And then I looked for which of these reduced. If only one of them reduced, that wasn't enough. But if both of them reduced, it turns out that I know both of these angles. So when we write this, I encourage you to write this step first, and then we will say cosine of pi over 3 plus pi over 4. And like before, now that this is written as the cosine of a sum of two angles, I can use the cosine sum angle formula that said cosine of the first angle, cosine of pi over 4, times cosine of the second angle, that means cosine of pi over 3, minus sine of the first angle, times sine of the second angle. And now these are things that we can evaluate. I know the cosine of pi over 4. Cosine of pi over 4 is radical 2 over 2. And I know the cosine of pi over 3. I know the sine of pi over 4. And I know the sine of pi over 3. And when we simplify this, we get something that involves an awful lot of similar stuff to what we've done with the last two examples. And the last step, as before, is to write this as one fraction. Notice that 6 is bigger than 2, so radical 6 is bigger than radical 2, which means that, like 3 minus 5, this is a negative number. Which is cool because 7 pi over 12 is in the second quadrant where cosine is negative. We expect to get a negative answer. I want you to be able to do this problem without having to use degrees. But to collect our thoughts, I would like you to turn this angle into degrees so that we can compare things. Go ahead, wait a minute, pause this, and calculate. Have you got it? 3, 2, 1, in degrees, 7 pi over 12 is 105 degrees. You'll notice in the calculations that I don't multiply by 7 until the very end, which suggests that 7 times pi over 12 is 7 times 15 degrees. So if you want to do a little bit of side work here, you'll notice that 15 degrees is 1 pi over 12. This is helpful. So 105 degrees, 7 pi over 12. What is the reference angle for this? Go ahead, find it. 3, 2, 1. The reference angle for the second quadrant is 180 degrees minus theta, or pi minus theta if you're in radians. And its reference angle is 75 degrees, the very first angle that we did. So hopefully you'll see that this, root 6 minus root 2 over 4, and this, root 2 minus root 6 over 4, are opposites. That the cosine of this angle in the second quadrant is the opposite of the cosine of this angle in the first quadrant. Here is 75 degrees, and here is 105 degrees, also known as 7 pi over 12. Because they have the same reference angle, their cosine values have the same absolute value. Observations like this and a little bit of knowing what to expect can help you check your work and make sure your answers make sense when you're doing things like this. So please keep things like that in mind. Please stay tuned for the future when I do different examples of how to use the cosine sum angle identity, and for the future where we do the cosine difference angle identity. The word of the day is Tellururus, the wicker tail dinosaur, wicker tail, and this has been a Badger Bear production.